Hi all, welcome to part 12 of the video lecture on counters. See here we will see a special counter called BCD counter. You know BCD number and all we already learned, right? The binary coded decimal. So in BCD we have digits like this is a normal decimal based system, right? BCD we have digits from 0 to 9. And if you want to express a number so whatever it is, so some number 22 you have to represent, 24 you have to represent this 2, then represent this 4, like that. So for 2 you will use the BCD representation 0 0 1 0. So this is a BCD representation of 2, and similarly for 4 it is 0 1 0 0. So basically in BCD every digit, individual digits of the number we will represent using 4 bits. So the normal binary only, but the problem is using 4-bit we have a range of typically using 4-bit we have the range from 0 0 0 to 0 0 1 0 1, like that, 1 0 0 1 0 0 1 1 0 1 0, like that it will go up to 1 1 1 1. But these things are invalid when it comes to BCD, right? But only these things are valid. So if you have the number say 12 in binary, you can represent it using something like this. So this is a binary representation of 12. But the same 12 when it comes to BCD, this 12 you will represent like 1 you take. See, take each digit, and what is the representation of 1? 4-bit binary, like this. So for 2 it is 0 0 1 0. This is the BCD representation of 12. Okay, BCD representation of 12. So this is what I was saying. So this is a BCD system, something we already know. Now I want a BCD counter, means I need the counting from 0 to 0 0 000. So basically I need a 4-bit counting, right? So it will go from 4-bit up counter. By default it will go from 0 to 15, but here I don't want to go up to 15. After 9 I need to restart from 0, like that. So that is the requirement. So that is a difference. So when it comes to BCD counter, we know that it is a 4-bit counter, and 4-bit counter there are 0 to 15, 16 different counting states are possible, and out of them 0 to 9 only 10 are valid. Remaining 6 combination I have to eliminate somehow, right? So that is my requirement. Accordingly I have to design the counter. So the BCD counter counts in binary coded decimal from 0 to 9 and back to 0. So that is important. After 9 the next state should not be 10, it should be 0. Because of the return to 0 after a count of 9, a BCD counter does not have a regular pattern of a regular straight binary count. Straight binary counter means sub counter, it will count from 0 to 15 counting states are there, right? That is not here. So to derive the circuit of a BCD synchronous counter, so by default we are discussing about synchronous counters only, where clock is applied to all the flip-flops simultaneously. So it is necessary to go through a sequential circuit design procedure. Sequential circuit design procedure means the state table method we discussed for upcounting. Shortcut and all, it's not possible for everyone. Like normal upcounting we saw some way to generalize it, but in a special case like BCD counting and all, you have to go with the normal method of state table, state transition, and how the flip-flop input should be there. So that method you have to follow. Okay, so you will see that state table of BCD counter in the next slide. Now the conditions for T flip-flops are obtained from the preset and present and next state condition. We will see that how to derive this T inputs. Also shown in the table is an output of Y, which is now that they are giving one more extra output of Y, which is equal to 1 whenever it reaches one set of counting, that is from 0 0 0 to when it completes a counting like up to 1 0 0 1, and that time this Y will be equal to 1. So why we are using this Y output, we will see that maybe sometimes. So by default it is a decade counter, right? So the BCD counter is also called, sometimes they may ask you in question, design a synchronous decade counter. So decade 10, right? So that is the meaning. So decade counter means it should go through 10 different states. That's the meaning. So here sometimes you want to implement something like a 3-decade counter, 2-decade counter. So more than one BCD counters you will use, and that time when to enable the second one, after completing one sequence of counting you can enable the second one, and that time this Y output is going to help. We will see that cascading of multiple BCD counter, and that time when to enable each one will be decided by this Y output. So in this way I can enable the count of the next higher significant decade. That is what I said. So right now we are going through one set of counting. Higher significant decade you can enable counting, and then so while the sample pulse switches the present decade from this to 0. I mean we will see that. Okay, yeah, this is the state table of a BCD counter. Just like what we saw for an up counter. If the present state is all 0, right, then the next state will be 1. If the present state is 0001, next state will be 00010, that is 2. So like that, 3, 2, then 3, 3, then 4, like that. So finally, when the present state is 1001, normal up counter, the next state will be 1010, I mean 10. But here the next state has to be 000. Okay. Now, accordingly you have to find out, whether you want a toggling or not. You have to fill the bits. 4 flip-flops you are using, right? The one flip-flop will decide what is the least significant bit. The least significant bit of the counter is this, and this is a more significant bit. And why they are using like that? Because BCD is basically 8421 code, right? So each output they are denoting like a Q1, and this output bit they are, it's just a notation, Q2. This they are denoting like a Q4, and this they are denoting like a Q8. Corresponding T input they will be denoting like a TQ8. Right, like that you have to find out what is TQ8, what is TQ4, like that. Okay, you have to find out. Now what is this 8421 code. Hope you remember this, because in as a combination, each bit position is having some weight like this, right? Suppose I want to express something like a 5. So what is 5? 5 is 4 plus 1. So the bit position 8 is there is no weight for that position. 4 weight is there, it should be present, and bit position 2 there is no weight, bit position 1 there is weight. So accordingly 5 can be represented like this in BCD. So this is a convention, right? The 8421 code. There are many such codes are there, and BCD is one code which is popularly known for like 8421 code. Okay, so accordingly the bit positions are given name. And fine, that's all. Now using K-map you will be simplifying this TK8 to each of this bit. So if I am asking you what is this TQ8, you will express it as a function of the input bits, that is Q8, Q4, Q2 and Q1. So you are supposed to find out what is every toggle input as a function of the present input or the input bits. Okay, so that you have to find it. So for that you have to use a K-map, right? Now in K-map, as there are 10 rows, there will be 16 cells. 8 cells are not enough, right? So now how you will fill the remaining entries? So these are all the entries like this is midterm 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So midterm 7 and 9 are 1. Now what about midterm 10, 11, 12, 13, 14, 15? So that you have to continue filling, like all those things are don't care, okay, in the K-map, because these are all invalid in our case. So if I am reaching, due to some worst case, I am reaching to something like 1010, so that is invalid for me. I want something from 0002 to 1001. Okay, so that invalid state, I mean the state diagram actually if you go through all the states there will be 16 states, but here out of the 16 only 10 are valid. Okay, so if you draw the state diagram, it will be like state 0, then state 1, then state 2, state 3, like that. Normally it should go up to 15, but here it will go up to 9 only, then it will go back. So what about state 10, 11? They are all invalid. But if you want, you can analyze these things and see, suppose in worst case, definitely circuit may reach to any of the invalid state. So in that invalid state, by default, the behavior is default. I mean, don't care, whatever it is, we can't do anything, because we are expecting a valid behavior, right? So but there are some way by which we can analyze a circuit, and we can see if due to any reason, if the circuit is reaching invalid state, with what valid state it is going through. If it is again going through an invalid state, then and it is circulating there, it will be complex for us. Anyway, that concept we will see maybe in the next video. So right now we are not worrying about the invalid state, we are just putting them like a don't care. So here also all these min terms, the corresponding terms are don't care. Here also it is don't care. So those things are not shown in the state table, but if you want in exam also you can show them. Okay, so suppose I am reaching somewhere like 1010, what I have to do? Next state I am not worrying about it, whatever it is, it's going to an invalid state, because it is not a valid state up to 1111. These are all invalid according to my counting, right? So they are going to go down gear like that. So now you can simplify it using K-map. So let me show you what about the simplification of TQ8. So TQ8 I am seeing, we have to use a 16 cell K-map. There will be 4 columns and 4 rows. And the labeling corresponds to the inputs Q8, Q4, Q2, Q1. 0 0 0 1 1 0 1 1. Here also 0 0 0 1 1 0 1 1, and numbering is like a 0 1 2 3 4 5. So if you do this numbering, it is very easy, right? That is why this is the way I am practiced with. But if you want, you can do without this numbering also. 12, 13, 14, 15. And now tell me, we are looking at a T8, right? It's TQ8. So it is giving a 1 for midterm 7 and midterm 9, and 10 to 15 it is giving down gear 7 and 9. 7 is 1 and 9 is also 1. What about 10, 11, 12, 13, 14, 15? They are all down gear. Now this down gear we will group only for making such some bigger grouping. Okay, so here these two ones are to be grouped. That is my target. So the largest group possible is one grouping is like this, right? This 4. If I am taking these two down gear, there is no use, because after 4 element grouping, the next expected combination is like 8 element grouping. That is not possible because this 8 is missing, right? This term is missing. Now what about this one? To cover this one, this is the possible one. You can't make it bigger group, right? So now what is the term corresponding to it? Corresponding to it, this Q8 is vanishing and Q4 is 1. So Q4 is there. And now what about Q2 and Q1? They are both 1. Right. Now what about this grouping? 1, Q8 is there. Q4 vanishes, and here at the top 0 to 1 Q2 vanishes and Q1 is there. So this is the expression, right? So one term I got is like a Q8 to Q1. And another term I got is Q4, Q2, Q1. Okay, so together that is the SOP expression for Q8. Now you can similarly find out the input for the flip-flop corresponding to the bit Q4, corresponding to bit Q2 and Q1. Q1 is definitely in the toggle mode, because last bit will toggle always, right? That that you don't have to depend. So don't draw the K-map for Q1, because that observation we know, because the continuous counting, right? That's definitely the last bit will toggle always. But there are cases where the sequence given may not be continuous. That time you have to be careful. That time you have to find a different expression for that. Okay. In case of continuous counting, you can, without looking at the K-map, you can write it as 1, because I want it to be in toggle mode always. Other two expression you please try yourself, like TQ8, how I am getting Q8 complement Q1, and TQ4, how I am getting Q2 comma Q1. And there is something called a Y output I told you, because Y output Q8 and Q1, 1 0 0 1, and this is your Q8 bit, then this is Q4, Q2, Q1. So whenever this Q8 and Q1 both are 1, this Y is getting 1. Okay, so that means whenever I am reaching this 9, so that time only these two bits are going to be 1, right? So you can see that the other, in any other case, these two bits are not going to be simultaneously 1. Okay, so that time I am saying like the current sequence of counting. So if I have a BCD counter, so this is the decade counter, right? BCD counter 1. Suppose it gone through all the counting like Q8, Q4, Q2, Q1. It starting from 0 0 0, it keeps at every clock cycle, right? It is counting like 0 0 0 1, etc. It gone up to 1 0 0 0 1, and at that point it will make this Y is equal to 1. And this say this Y output, if this is a Y output, this will act as an enable input for the next BCD counter, right? BCD counter. Okay, so that will count. So now it is like a 2 decade counter. So if you want to extend it to 3 decade counter, take this Y output and apply to the next one. So like that you can cascade multiple counters, or simply take that Y, how many times is Y is getting 1, like that you can decide how many clock pulses are over, like how many timing signals are over. So like that it finds application inside the circuit design. Okay. inside any logic circuit. So that about it, and then you can draw this diagram in exam. It is always better. Writing up to this equation writing is the main thing. After that you can just draw a small diagram also, because sometimes they may reduce the mark if diagram is not there, some 1 or 2 marks will be reduced, that you don't want, right? So you can just draw the diagram also, but this equation is mainly people will be looking like whether you got the correct equation or not. So that this is very important to highlight the equation, and after that give a small circuit showing that this is how the circuit implementation will look like. Okay, so the idea is clear. Hope it is okay for you. Like what we saw is the BCD counting, the binary coded decimal counting, or decade counting is another name. So it's just an up counter, but not like the ordinary up counting where it's go through all the possible states. Here it will go from 0 to 9 only, right? So 10 different states it will count, and after that again it will reset to 0 and it will continue up to 9. So like that counting is happening. So now some of the states are getting invalid, and we know how to eliminate some of the states. Now the question is, can you eliminate some of the states in between? Like here 0 to 9 still we are getting as continuous, right? Sometimes I am giving you some random sequence, like I want to count like 0, then 1, then 2, then I don't want 3, I want 4, then I don't want 5, 1, 6, I want 7, like that. They can give you any sequence. So given any such random sequence, are you able to come up with the counter for that? So that is a topic of interest, and we will see that in the next slide. Okay, we will see how to come up with a counter where some of the in between states are invalid, or they are not there as part of the final counting. Okay, yeah, thank you. Doubts, if any, you can ask me.